Okay, we're looking at Module 5B, still looking at open systems, and today we're going to talk about nozzles and diffusers. It's a type of open system. Throttling devices, which are valves, and turbines, which produce power for you. So you're familiar with nozzles and turbines, like the nozzle on your hose will take the velocity from a low flow coming out of an open hose to a high or a low velocity coming out of an open hose to a high velocity when you pass it through the nozzle. And a diffuser is just the opposite of that. It goes from low velocity to a high velocity to a low velocity in a diffuser. So again, we're talking about open systems and some examples of open systems. Let's first of all look at subsonic nozzles and diffusers. They'll generally, in a nozzle, you'll have the area getting smaller, and so the velocity will increase because the velocity times the area is equal to volumetric flow rate, as we recall from earlier. That's for continuity of flow. The mass flow stays the same from point 1 to point 2. Now we could take that same fluid as we put it through the nozzle and speed up the velocity, put it back through a diffuser, which has an increasing area, so the velocity slows down. So we'll look at nozzle diffusers. And we're going to assume that this is a steady state system. So steady state, remember with steady state, the change with time of the system, of all the properties within the system, is 0. So there's nothing accumulated in the system. We'll assume it's running at steady state. There's no change of the system itself. So in is equal to out for our energy balance and for our mass balance as well. Okay, here are the equations we're going to use. Recall that for open systems, the energy going in with the mass is the H, which is U plus PV, plus any kinetic energy per mass, plus any potential energy per mass. And we'll suppose that there's a Q coming in, although often we'll insulate it and make that Q 0. But suppose there's a Q coming in, we'll call that Q dot, heat energy per time, plus mass times the energy per mass going out. Mass times energy per mass at the outlet. This holds for both nozzles and diffusers. So what I like to define is a Q per mass, Q over mass, and I'll use a small q for that. It's not specific because it's not a property, but it's the heat per mass is delta H plus delta kinetic energy per mass plus delta potential energy. And you see this as Q, H2 minus H1 plus V2 squared minus V1 squared. Potential energy change in a nozzle or diffuser is going to be approximately 0 because there's a fairly small devices and you're not going to have a large drop in elevation as you go through the device. So mainly changes in velocity and changes in enthalpy. And again, often the Q will be 0. Notice on these devices that the work is 0. There is no shaft, nothing external to the system. It's just a simple, let's say looks like a cone or a truncated cone. Nothing external to the system to receive the work. The changing energy of the fluid goes to changing its velocity and not to producing work. So what you have is something that will speed up your velocity but will not produce work for you. Now, the change in velocity will result in a net force because you have an acceleration of the mass. And you recall one of Newton's laws, force is equal to mass times acceleration. And so when you put a nozzle in place, you've got to make sure you have something holding it in place, or it will try and accelerate the whole system. The change in the velocity will try to accelerate the whole system. In fact, we use that often to accelerate the, well, here's one where we're holding it. Suppose we're holding the hose, securing the hose, and then the velocity speeds up. Or we can have the situation where the velocity is used to accelerate the system itself. And so NASA we'll use nozzles on the rockets. Now those are supersonic generally, and so you'll see it's interesting that those nozzles are reversed in, they're actually a diverging nozzle. The area is getting larger even though the velocity is going up, and that's what happens when you get beyond sonic velocity. Now valves is something that we'll use a lot as we go in and look at systems. When we start putting these things together, valves we'll use a lot. Now throttling process is an approximation of what goes on in a valve, so we'll look at throttling processes so that we can model valves. A valve takes a fluid at a high pressure, comes out at a low pressure, and here's what it may look like. You have a restriction in your line that causes the fluid to have to change directions, and what happens is the pressure drops as you go through the valve. Restrictions in the line, and the assumption here with the valve is that the velocity change is negligible. Now here's a word we haven't seen much of: irreversible. They're highly irreversible. You can't make it go backwards. Like for instance, if I put once I pass this fluid from the high pressure to the low pressure, it would be impossible really to turn it around and make it go back up the other way. It's irreversible. I've lost actually the potential to do work because I could have spun it around a fan blade or some kind of blade and produced work from doing this, but I did not, and so we call this irreversible, and accordingly mechanical energy or mechanical potential was wasted in a valve. So valves are a somewhat wasteful kind of device, but we use them for many reasons. Okay, let's look at the energy balance on the valve. In equals out, no accumulated. I mean, there's no place in the valve for the fluid to hold up, and so the energy, once you get the valve, once you have fluid flowing through there, it'll come to steady state fairly quickly. Valves are usually small compared to the amount of fluid that's going through them, and so you'll reach a steady state in a valve often, and so it's a good approximation to say in equals out that operates at steady state. So the energy balance on the valve, mass times the energy per mass in, should be looking familiar, plus Q equals the mass times the energy per mass out. Now valves, we often say, are adiabatic. Remember, adiabatic means Q is equal to 0. That's because the surface area of the valve is very small. Again, valves are small usually compared to the amount of fluid going through them, and so you need surface area to transfer heat. Take a look at your radiator and notice that it has a lot of surface on it. That's in order to transfer heat to the air from the liquid in the radiator. A valve has very little surface area, so it's going to have very little Q, and so accordingly the energy balance reduces to, now we're neglecting kinetic energy changes, and that's really the definition of a throttling process, and we're neglecting potential energy changes, and so we wind up with a process where H1 equals H2. Now that's kind of handy because that gives you an equation to describe a relation between two states in your process, and when we're analyzing processes we're always looking for a link between states in a process. Okay, we've considered flow devices with no moving parts, no shaft to capture or deliver mechanical energy. So let's imagine what we could do if we took that high pressure flow or high pressure fluid and then let it run across a blade of some sort. And that's what we call a turbine. We'll take a fluid from a high pressure, bring it into the turbine, and run it across the blades of a turbine. So you go through the turbine, spinning those blades as it goes through. Turn those blades. You've heard of wind turbines. They basically do the same thing. You go through the turbine, and the blades are spinning, and since the blades are spinning, I've created mechanical energy, rotational energy here, and that could be used to lift a weight as I've diagrammed it here. Most of the time we're either running a shaft directly to, like on an aircraft carrier. Some of these turbine shafts go directly to a propeller, maybe through a gearbox, and some of them will go to a generator. So many turbines will go to an electrical generator to generate electrical power, or just use the mechanical power directly. The energy balance, in equals out, and so we have mass flow in times the energy per mass in plus any Q that might be going in. Usually in a turbine the Q is going out, but you can draw it on the left hand side or the right hand side depending on what you think is happening, and is equal to the mass flow times the energy out plus the work out. When you're taking a fluid and going from a high pressure to a low pressure, then you're getting work. So the natural flow of fluid is from high pressure to low pressure, so you can stop it along the way, sort of dam it up if you will, and that's how the old water mills worked. Dam it up and you can produce power. Work will come out of that. Let's look at an adiabatic turbine first with a low velocity, or low change in velocity. The elevation change, again the potential energy change is very small because it's a fixed elevation turbine. You don't have very much drop in elevation in these things, and so the potential energy change is small. The kinetic energy change, if we have low velocity changes or low velocity in and out, then the kinetic energy change will be small also, and so you wind up with a fairly simple energy balance. Mass flow times H in minus H out equals work produced. Now that's again an adiabatic turbine where there's no heat lost from the turbine. And in fact, in a power plant, what you'll do is you'll insulate the turbine to make sure you don't have any energy lost, because that's kind of a loss of your power that you're trying to produce. Let's take an example. Suppose we have air at 1340 K and 11 bar, and expand it through an adiabatic turbine to 800 K and 1 bar. You're going to produce 75 megawatts of power from this turbine. The question is, what is the required airflow? And to solve this problem, we just take work equals mass flow times H1 minus H2. Put in for an ideal gas. We'll treat air as an ideal gas here. Cp times T1 and minus T2. I'm going to take the Cp as 1.15, which for this temperature range is about the average of the Cp over that temperature range. So I'm just taking an average Cp here, times the delta T, well actually T in minus T out. Set it equal to my power that I need to produce, 75,000 kilojoules per second. Multiply it times that delta H calculated from the ideal gas equation, and I can solve for m dot. M dot equals 121 kilograms per second. So fairly simple problem. Now let's suppose I want to explore to see with this situation what exhaust area I need to limit the velocity to 60 miles per hour. Again, I said low velocity, but let's suppose it wasn't so low. I had 60 miles per hour coming out of it, of the turbine. What exhaust area do I need for that particular turbine? By the way, that's 27 meters per second if you do the unit conversion. Want to know the cross-sectional area. Well, this is a calculation you want to be able to do to be able to calculate velocity from a volume flow. Well, we know mass flow. We know the mass flow, we just calculated it. I think it was 120 something kilograms per second. And we know that PV equals nRT, and so at the exhaust I'll take the pressure. I know the temperature was given in the problem statement, and then I'll solve for the cross-sectional area from that equation. Just solve your ideal gas equation. By the way, I'm setting the velocity times the cross-sectional area as the volume flow, and volume flow is going to be proportional to your mass flow. So mass flow times RT divided by P molecular weight times velocity. Plug in all my numbers and I find out that I need, at the exhaust of that turbine, 11 feet diameter. So that's a fairly large duct in order to accommodate that velocity. If I try to put it through a smaller duct, it's going to be going even faster. Okay, let's take another example. Let's take, instead of using air, and I want you to be able to do turbine problems using air with ideal gas equations, or any ideal gas with ideal gas equations. And I also want you to be able to do turbine problems using steam or a refrigerant, let's say. Something that you have tables for. So remember, when we found properties, we used either equations or we used tables. If I had a steam turbine, I'd go ahead and use my tables. So suppose I had steam at 640 degrees C, 10 bar, and expand it to 1 bar and 360 degrees C. That's a similar pressure drop as our last problem. And notice the temperature is dropping as I expand it. You're taking energy out of it. So the temperature will generally drop as you remove that energy until it gets to saturated. But even once it's saturated, if you keep dropping the pressure, the temperature will drop also. So let's suppose I have an adiabatic turbine produce 75 megawatts, just as the prior turbine with the air. And let's see what the required steam flow is. Okay, so I'll take my properties, set up a table for my properties, and I've given you two properties in the problem statement. 640 and 10 bar gives you an H of 3787. 360 and 1 bar, H is 3195. So the difference in those H's times the mass flow would be equal to the work flow. So again, W dot equals M dot H1 minus H2. And we solved that from our energy balance. So the mass flow solving is equal to 127 kilograms per second. Actually, that's fairly similar to what we had before. Now it's convenient to look at work per mass, because often we'll get into problems where we're having to go through several steps. We'll have processes where there'll be several states, and we want to analyze those processes without the mass, and that's, well, you'll see later, that's a convenient thing to do. So I'm going to define work per mass, or work per time divided by mass per time, as the work per mass, and I'll give that a small w the way I did a small q earlier. So H1 minus H2 in this case is 591.3 kilojoules per kilogram. That's just our delta H, and then scale the problem to the load size. So the work per time, this is just a convenience trick that I use, work per time is equal to 75,000 is equal to mass per time times work per mass. So that's something we'll use quite a bit later on. Often if you're working problems from your text, they'll be asking for the work in BTUs per pound mass or kilojoules per kilogram. And so you know what they mean by looking at the units. You know what they mean is what is the work per mass in that process. Okay, I just want to go back to what we talked about properties, and we can calculate what the average CP was for the steam in this process. And you see that CP is equal to delta H over delta T. Now this was at a changing pressure, and it's supposed to be at a constant pressure, but if we treated the steam as an ideal gas over this interval, and if you look in your tables you see it's a gas at both states, then and the pressures are fairly low here, then delta H over delta T will be equal to CP whether the pressure changes or not. Remember, for an ideal gas, dH equals CP dt. So I'll calculate the CP, and I find that it is equal to 2.11 kilojoules per kilogram, whereas the air was considerably lower CP. I believe it was 1.15, and so pound for pound, steam is a better working fluid. I can get more work out of the steam over a smaller temperature drop. And you'll notice that 640 minus 360, I believe our other problem was, I think it was 1100 to 800, something like that. Quite a bit more drop in temperature. Okay, last thing I want to do with turbines is suppose we had liquid going through a turbine. If I put a high pressure liquid into a turbine, and this is done in hydroelectric plants. If you have a river and you dam it up, then you'll run the liquid through a turbine. But because the volume isn't changing, you get much less work per mass that's going through the turbine. So let's take water at 10 bar and drop it to 1 bar and ask what the work is per mass. Here's our turbine. Work again for a turbine. If it's adiabatic, H1 minus H2. And again, we're neglecting kinetic energy changes. And recall that for liquids, we had that delta H is equal to V delta P, assuming that the temperature isn't changing. And the temperature won't be changing much in these liquid turbines. So we'll take that 0.001 times delta P. I have it in bars here. So you've got to be careful in order to compare this to our other result, which was kilojoules per kilogram. I have to convert it to Pascal bars. I believe, let's see, a Pascal bar will give you your kilojoule, let's see, per kilogram, or joules per kilogram. Yes, kilopascal bars is a kilojoule per kilogram. Okay, that's not much work. So in order to produce power from a liquid, you've got to have a whole lot of liquid going through pretty good pressure drop. And so like you take the Hoover Dam or any very large dam, and you've got a whole river flowing through it. So you've got a lot of flow and you can produce power, but not as much as you can when you're expanding a gas pound for pound. Okay, so we looked at nozzles and diffusers. You can have problems on those. Nozzles, the velocity increases. Diffusers, the velocity decreases. We looked at throttling devices, which are valves. And capillary tubes also act as throttling devices. And you'll find those in your refrigerators. And again, for the valve, the enthalpy is constant. So for a throttling process, let's say, which approximates a valve, enthalpy is constant across the device. So delta H is 0, or H1 equals H2. And we looked at turbines. The power output is primarily from the delta H, although you will see some problems, and you'll have problems to work where there is a change in kinetic energy, and you have to consider that too. And there also may be Q if it's not well insulated. So for your homework, what I'd like you to do is work problems in Chapter 5 involving nozzles, valves, and turbines. Work as many of those as you can, and just start to practice and become proficient at doing these energy balances.